A particle moves such that its position vector r as a function of t is cos omega t plus cos omega t I cap plus sin omega t j cap, where omega is the constant and t is time. Then which of the following statement is true for velocity v and acceleration of the particle? See, this can actually be solved in the classical way, wherein actually you will differentiate this function and then find velocity vector as well as the acceleration vector and then look upon these options. Or what we can do directly is you find out the magnitude of vector r. So say for example, what is magnitude of vector r? Magnitude of vector r is equal to root of I component square, which is cos omega square t, plus j component square, which is sin omega square t, right? So what we get here is magnitude of vector r is equal to 1, right? So what is vector r? Vector r is x plus iy, or sorry, is x I cap plus y j cap is vector r. So now if you take modulus on both sides, what you get is modulus of xi plus yj is equal to modulus of r. Now what is modulus of r? It is 1. What is modulus of root xi plus yj? It is root of x square plus y square. Which means if we square on both sides, what you get is x square plus y square is equal to 1. So I'll rewrite this equation. I'll write it as x minus 0 the whole square plus y minus 0 the whole square is equal to 1 square, and then I will compare this with x minus a the whole square plus y minus b the whole square is equal to r square. And what do I get? I get that a comma b is equal to, so a is 0, b is 0, what I get is 0 comma 0, and what I get is r is equal to 1. And what is this? This represents nothing but equation of a circle with center being the origin, center o comma o, and with radius equal to 1 unit, right? Now, yes, we have crossed the 2-minute time limit that we have set for the question, but anyway, I'm explaining the process here, right? So it will definitely take some more time. I'm not solving it, I'm explaining the solution. So if this is the case, it clearly means that we have a circular motion in our picture. So now we have an object exhibiting circular motion. Maybe now we can start counting the time. So what we have here is, we know that this is position vector r, right? Assuming to be the let us say the clockwise direction, we know velocity vector here would be vector v, right? And we also know that this will be the direction for centripetal acceleration, and this will be the direction for tangential acceleration, right? Now let us try to solve the question. V is perpendicular to r. Is V perpendicular to r? Yes, we know that this angle between this velocity vector and radial vector is 90 degrees. That's correct, and is directed away from the origin. So, and a is directed away from the origin. See, acceleration, this is origin, right? This is 0 comma 0, and this is how the direction of acceleration vector is, right? It is actually directed towards the origin, not away from it. So this option is wrong. V and A are both perpendicular to r. No, V is perpendicular to r. But is A perpendicular to r? No, A is in fact parallel to r. The angle between them is 0 degree. V and A are both parallel to r. No, V is perpendicular to r and A is parallel to r. So that option is wrong. V is perpendicular to r. True, we know. And A is directed towards the origin. We just saw this is how it is directed towards the origin. So this is the correct option. Now, I would like to go a bit further to explain or just to discuss some of the graphs that I feel is really important since that we have arrived at this topic. So the very basic graph, what we need to understand here is, right, the very basic one is that if we have a counterclockwise motion, let's say a counterclockwise motion, and a clockwise motion, let us analyze these two. So this is circular motion, this also is circular motion. Counterclockwise means this is direction of motion, clockwise means direction of motion would be like this. And in both cases, let us analyze this point A, center being O here. We know that this is the direction of displacement vector, vector R. This is the direction of displacement vector, the direction of a position vector, vector R, right? Not the displacement vector, the position vector. Now, if the velocity is acting counterclockwise, this is how the velocity vector would look, perpendicular to the position vector. This is how the velocity vector would look here, tangential at this point, perpendicular to the position vector. Okay, so that is one graph. The second graph would be the relationship between tangential acceleration, right? Tangential acceleration, centripetal acceleration, and velocity vector. When I say velocity vector, I mean linear velocity vector, vector v. Okay, so let us try to understand that too. So we're going to circle here. So we'll have three cases to be analyzed here. Okay, what are these cases? We'll see one by one. So in the first case, okay, first let us draw the direction of centripetal acceleration. So this is center O, this is center O, this is center O, and in all three cases, centripetal acceleration is always directed towards the center, right? Centripetal acceleration is always towards the center, let us say towards the origin. Now, how will be the velocity vector? The velocity vector, okay, now I'm not going to take two different cases of clockwise and anti-clockwise. What I'm going to do is assuming it to be counterclockwise in all cases. So this is velocity vector, right? This is velocity vector. And let us say this is velocity vector again. Now what do we see here is another component of acceleration, which is the tangential acceleration. So one case is that the tangential acceleration is actually equal to 0, which means there is only AC acting. So acceleration net would be equal to AC plus AT, right? And AT is 0, therefore the net acceleration would be equal to centripetal acceleration alone, right? Now moving on further, in this case, the second case, what we'll assume is another vector, tangential acceleration, acts along the velocity vector. Okay, in this case the net acceleration, so this is centripetal acceleration, and this will be the resultant acceleration of AC and AT. So this will be the direction of net acceleration, right? Another case, when the tangential acceleration is against the motion of the direction of velocity, which means acceleration is acting opposing to velocity or decelerated motion. So this is AT. What we have here is acceleration centripetal, in which case we know that this would be the direction for A net, right? So I hope these three directions are also clear. Let us now discuss one more point, which is based on say angular velocity, direction of angular velocity. Direction of angular velocity. How do we assume that? Let us see. So we got circular motion here, right? So let us see direction of angular velocity versus that of linear velocity. That will make the concept even more clear. So what we have here is origin, okay, and say this is the direction, the position vector r. This is the position vector r. And since we have the position vector here, sorry for the interruption. Yeah. So let me the position vector r. Now what we'll see is, okay. So this is counterclockwise motion, right? Velocity vector here. Then we have velocity vector over here, which represents the clockwise motion. So this is counterclockwise. And this motion is the clockwise motion. Now let us see the direction of angular velocity. So if counterclockwise direction, angular velocity vector would be heading like this, omega. And here angular velocity vector would be acting like this, down towards the plane, omega. Okay. Now to have an understanding about the coordinate axis, let me try to draw this diagram in a planar basis. So say if we represent this coordinate axis, okay, so let us say okay, so we have, right, so we have the axis like this, okay, say x, say y, and say z, okay, and this is how the circular motion is taking place, all right. And say from origin, this is the velocity or position vector r, and let us assume that the motion is taking place in a counterclockwise direction. This is linear velocity vector v. In which case, see what is the meaning of, what is the physical meaning of v cross r? V cross r basically implies that is a new vector. It's actually a third vector which is perpendicular to the plane containing x and y. I'm sorry, the plane containing v and r, such that it is perpendicular to both v and r, which means we need a new vector here like this, which is perpendicular to the plane containing. Now what is perpendicular to the plane containing? What is the plane? The plane is xy plane. So if a vector is perpendicular to xy plane, how should it direct? It should move along the z axis, and that is how we get the omega vector like this. Okay, so that's it with direction of angular velocity and linear velocity. Now I would like to introduce one more graph here, a diagram here, which would be the discussion for let us say angular acceleration, right? Angular acceleration and okay, so angular acceleration and angular velocity. Let us discuss that also. Angular acceleration and angular velocity. So while discussing angular acceleration and angular velocity, we'll make use of a diagram again. Circular motion again. So center O, center origin, and then position vector R, position vector R. So we'll try to understand this using two different cases. Case 1, the rate of rotation increases, and in the second case, rate of rotation decreases. Both of it's taking place in the counterclockwise direction. Okay, both of this is taking place in the counterclockwise direction. For example, clockwise direction. So this is how what we see. This is the direction of motion. Okay. In which case, how would the vectors look? So we know that the angular velocity would be perpendicular to the plane. So we have angular velocity omega here. Angular velocity is perpendicular to the plane. We have angular velocity here. Okay. Why won't the direction change here? Because we know that since being in the counterclockwise direction, this is the direction of velocity. This is the direction of velocity. So omega will remain the same. But how will the direction of angular acceleration vary? See, for that what we need to understand is angular acceleration would be along the same direction of angular velocity omega. So alpha is along omega. But in the second case, what happens is alpha is acting downwards. Why? Rate of rotation decreases, there is deceleration, which means rate of acceleration will be, angular acceleration would be acting downwards. Rate of rotation increases, acceleration, direction is towards the positive z axis. Okay. Now, having said this, let us also try to understand the relationship between angular acceleration, right? Angular acceleration and linear acceleration. Circular motion, center O, position vector R, position vector R, position vector R. Now we know that this is the acceleration vector. This will be alpha, right? How here? So alpha here is basically vector R cross A, which is actually a third vector perpendicular to the plane containing R and A. Simple concept again. Now, this will take place when the motion is counterclockwise, but when the motion is clockwise, we know that the acceleration vector would be acting like this, right? This is acceleration vector. And how will the angular acceleration look like? Angular acceleration would look, alpha would be perpendicular along the positive z-axis, right? So those are the comparison between the various diagrams, which would help, maybe we should help you further in solving the questions in maybe in the advanced or maybe in the NEET level. No, it's good to know that, good to know about all the possibilities of a specific motion while you prepare. Alright, so that's it with the concept of circular motion and the various the direction of vectors in circular motion. Let us move on to the next question. Okay, so before we go to the next question, I have arranged the diagrams, all of them together. So if you want to take down, that might help you. So let's see again, once again, what do you have here? We have the direction between angular acceleration and angular velocity, right? Omega and alpha. Angular acceleration, linear acceleration, alpha and A. Tangential acceleration, centripetal acceleration, AT, AC. And we have direction of angular velocity versus linear velocity, which is omega versus V. So hopefully I think I have explained all the cases for the clockwise as well as the counterclockwise direction. This would be enough. Okay, now let's move to the next question.